Good morning, everyone, or good afternoon if you're located east of the Mountain Time Zone. I know we've got folks from a wide range of locations across North America attending the event today, so thank you. Welcome to our webinar on climate risk and resiliency planning, hosted by Stantec. My name is Jason Dupay. I'm a vice president with Stantec based in Calgary, and I'll be moderating the session today. Just a few words about the agenda and housekeeping. Our 1 hour live event includes 2 presentations, followed by a panel discussion in which we will be discussing various aspects of climate risk and resiliency. So before we begin, I want to focus or to explain the process for asking questions during the webinar. When we sent out the invite, there was the opportunity for you to respond and provide questions back to us. We've got a number of questions from those in attendance, and thank you for taking the effort to put those together. There'll also be an opportunity to pose questions to the panelists during the webinar itself. If you go to webinar question box that should be on your screen, you can pose questions in the question drop-down menu. Please submit those questions, as many as you want or you need to, and we'll do everything we can to ask those questions of the attendees at the last 20 minutes of the event. If we don't get to your question, please feel free to reach out to the attendees or to the presenters, and they should be able to follow up with a response to your question. We'll have the contact details at the end of the presentation. Just wanted to say that both our presenters will have a short poll as part of their presentations at the end of the presentations. A good opportunity for you to participate and for us to get some feedback on some important questions. And finally, we'll be sending out a link of the event, which will be recorded and is being recorded for all those in participation, which could be shared with others as well. I want to take a minute for a safety moment, and wanted to talk quickly about flooded roads. Given the topic that of the event, we're seeing a number of high rainfall events, across North America. Lots of examples of that. Certainly here in Alberta, we've seen that with major flood in 2013 and a number of other subsequent floods and high rain events. So I just want to highlight a few important points here. So first, if you do come across an area where the road is flooded, don't drive into the flooded roadway. Please stop, turn around. It's noted here that just 12 inches of water can affect driving, and rushing water can carry away a small car, while 2 feet of rushing water can carry away most vehicles. Water may be deeper than it appears and can hide many hazards, including sharp objects, washed out road surfaces, electrical wires, chemicals, and other things, other obstacles. And many of the deaths that occur in automobiles are, from flooding as they are swept downstream. So it's never safe to drive or walk into flooded waters. So please be cautious and follow these directions. Thanks. So I want to quickly introduce our 2 presenters today. First, we have Norm Shippee. Norm is the National Technical Lead for Climate Change and Resilience here at Stantec. Norm has 12 years of experience in consulting and academia, and he's worked across most sectors, all levels of government, and most of the sectors within the private sector as well, focusing on improving climate resiliency for assets, services, and business needs. Norm's presentation will be followed by Curt Bjurlin. He's the Vice President with our power sector based in the US, and he's responsible for both conventional and renewable power sector work across the US, and is also heavily involved in the energy transition. So at this point, I'd like to turn it over to Norm. Thank you.
Thanks, Jason. And so I will be speaking today essentially on why climate resilience and climate risk is an issue. And so today, one of our major concerns here is why should we care about climate change and climate change risk? And how do I handle this within my day-to-day operations or in my asset planning and management? So there are many reasons to address climate change risk. And the first here that we have on the list here is really thinking about why we use infrastructure. It's really as a service. So our idea here for minimizing our infrastructure risk to climate change are really centered around things like minimizing service disruptions, protecting people, property, and the environment, optimizing service, managing the life cycle of our assets, reducing and avoiding costs, adding information on resiliency and adaptation planning, and also avoiding kind of these unplanned interventions that you may not expect due to climate change and climate-related events. So part of the reason that we're thinking about this is that infrastructure vulnerability to climate change is very different than it has been historically. For a long period of time, climate has been relatively stable. And in the recent 100 years or so, recent century, we're seeing rapid changes that we haven't seen historically, at least as long as we've had kind of our built infrastructure. So it matters for our planning, our design, our financing, and our operating and maintaining of our assets and our services. Historically, we would think about things as the past is the future, and we'd use that to design, operate, and maintain our assets. But the reality is that changes are occurring at a much faster rate. The current trend and current projections of future climate show that the rate of change is much faster than anything we've seen in the past. And so that gives us some sort of unquantified risk, some not understood what that impact might be on all of our assets. So the process we're going to talk about today talks about how to handle climate risk and improve your resiliency of your assets through a couple of different lenses. In terms of future climate uncertainty, this is handled by projections. And so climate and climate science used what we call models and climate projections to understand what future possible scenarios look like. These projections essentially are all showing things like increases in extreme events. So examples there would be things like short duration and high intensity rainfall events, changes in precipitation patterns, maybe rainfall, drought, or water balance issues, and increases in the number of high temperature extremes and extreme heat associated events such as wildfire and drought. On the right hand side here, you see a figure that shows a number of different scenarios. These are kind of based on global average emissions. And so over time here, the scenario that we've been tracking along, which is shown in the black dotted line here, that's our historical global emissions of carbon and GHGs. And we're tracking along this RCP 8.5, which is just a fancy way of saying kind of our business as usual scenario for our future projections. And that represents quite a bit of temperature change. So the opportunity and the risk here is really centered around building resilience. And we want to approach kind of the physical vulnerabilities of climate change by understanding our exposure to all different types of parameters, so that we can then identify risks and adaptation measures for all of our assets or infrastructure, and then also understand if there are risks posed by potential third parties areas. So if you're a company and you have a supply chain, does your supply chain have a resilient factor to it where you have either redundancy, or how exposed are your suppliers? The same idea with communications or fuel, like having an adaptation measure there for third party and understanding their risk. And the opportunity here with all of this is to improve the resilience of your assets for future climate conditions, and at the same time reduce overall operating costs and potential losses. One other bit of resilience here, or context, is essentially thinking about the way that design parameters have been used in the past. And we think about codes and standards as being based on historical data. And historically, that's the way that we've approached this problem, is looking at, say, a 30-year average period, understanding what the different representative conditions are, and using our codes and standards looking forward using that last 30 years. The challenge that we have here is with the rate of change of climate, we're really not able to use our previous codes with the same level of confidence that we have been able to in the past. The example that we show here on the right is showing kind of an example from codes and standards defined along a 30-year period, but you can see the different climate scenarios, and noting that we're tracking along this kind of business as usual red line here, those codes and standards will be less representative the further into the future that you go. And so the idea here is that codes and standards are needed to be revised on a regular basis, on the order of maybe 10 to 20 years, so that we can actually incorporate how fast climate is changing. And the image here on the right is showing you essentially the types of periods that we need to understand where future climate might be. And the types of parameters that are being updated within the codes and standards are really related to all different types of temperature and temperature-related parameters, like heating and cooling degree days, if you're thinking about buildings, perhaps design temperatures and max, mean, and min temperatures as well. But then around precipitation and moisture, we think about things like annual or 1 day or even short duration high-intensity rainfalls of 15 minutes, and things like wind-driven rain. And as we get further and further down the list here, things like snow and ice, those parameters are changing faster than our historical information can catch up to it. So the idea here would be that snow load information can be projected and updated regularly. So to approach resiliency within the process here, we have essentially a six-step process that ranges all the way from a hazards assessment to our adaptation planning. The steps essentially go from left to right here, starting with a hazards assessment to understand what hazards might my assets or services be exposed to. And then we take our assets and we understand what assets are we actually going to assess. By identifying those two key components, we can then understand what are the impacts if these hazards were to show up and affect our assets. And we then move into what we call consequence scoring. So consequence scoring allows you to understand, kind of on a ranked system, how severe is the impact if this were to manifest. All of this gets transformed together into our final risk assessment, where we combine kind of all of our information about consequence and impact with the likelihood of the hazards occurring. So we select specific hazards and we understand how frequent they are in the past and into the future. This can lead into an adaptation planning approach and then resiliency measures that come out of that. The overall idea here for the risk assessment process is that we would have kind of a threat and elements that are at risk. So I'm going to walk you through here kind of the typical conceptual model. The threat here could be something like a flood, or it could be an extreme heat event, and our elements at risk could be any bit of infrastructure, buildings, facilities, or even environmental activities. So our first question is, are we exposed to that threat? Are any one of these assets that we have exposed to that threat? And we'll do this for every single threat that we identify with future climate or current climate. If we're exposed to that threat, we then ask ourselves, what's our vulnerability if that threat occurs? Is it very, very high, or is it relatively minor? That allows us to assess what our consequence is if that hazard were to materialize. At the same time as all of this is going on, we're understanding essentially the likelihood of occurrence of those threats. So we might have an intensity threshold. We're worried about extreme heat over a specific temperature, for example, that we would understand how frequent is that happening now and into the future. And we combine all of those together into a likelihood multiplied by the consequence that we have to get a risk. What this turns into in the end is kind of a heat map. And this heat map here is showing you kind of different colors for different levels of risk. So green here would be something that's low risk, and red and orange would be high and extreme risk. We're really concerned with the top right quadrant of this heat map. Any events or interactions that wind up in this area are usually areas that we need to start making our first adjustments when it comes to adaptation and resiliency measures. So we're going to use the example of a flood. And at the moment, what we've done is we've ranked this flood with a consequence of a 5. So what this might mean is that a 5 here is very, very severe, could mean that we've destroyed some of our infrastructure, whereas a 1 would be something that we live with every day and it's not a big deal. So if something is super catastrophic, then it would rank in this 5 category. And then on the probability side, something that's a 1 is very unlikely, but still occurs. So maybe this is a 100-year or 150-year flood, whereas 5 would be something that occurs probably every year or we're used to experiencing. So in our example here, we're saying that our flood is extremely severe, but often rare. But climate change being introduced into our equation here is making that flood occur much, much more frequently. And assuming that we haven't taken any mitigation measures or adaptation measures here to improve our resiliency, we're going to wind up going from something that is probably a moderate risk to us right now to something that's an extreme risk because of climate change. And the only thing that we've done is influenced our probability based upon our change in climate. So how do we handle this issue? That's where we start to introduce adaptation measures to bring us back down to a much more manageable level of risk. And that example here would be that we might introduce, new barriers to prevent the flooding from occurring in such a large area. And so that would bring our consequence of impact back down to almost well below what it originally was. So the way these classifications happen, it's essentially a scale, and this scale can change depending on the assessment that you're doing. But in general, anything that falls into the high or extreme risk are where we start to have high or immediate controls for adaptation and resiliency measures right away. That's not to say that things that are in the green or blue category should be ignored, as sometimes something that is negligible or low risk, if added to something that is a moderate risk, can pose you a much higher risk than initially thought if you treat them as tandem events. So I'm going to show an example of how this has been applied and what the process looks like when you walk through it. We're going to use an example here of a client that was interested in doing a risk assessment for climate change due to issues that they've had with recent severe events. In this case, we were talking about tornadoes, freezing rain, and wind that were major issues for their distribution system. And so this project would look to complete an assessment of the distribution system and its vulnerabilities to climate change, look at the risk, and develop an adaptation plan. In general, the infrastructure that you look at can depend on the type of assessment you're doing. You can do this at a very high level, or you can go very, very in depth. For example, here we had a whole bunch of different categories ranging from buildings to third-party services. And we've broken out here kind of on the right-hand side an example of what the substations look like when we break out all the components that we're considering. So for example here, if we look at the station PC cabinets and batteries, we're looking individually at climate interactions with each of these individual components. But if you were going to take this at a higher level, you could take these smaller components and look at it as a whole. So if you're concerned about the buildings, you might just look at buildings by themselves instead of all the different pieces that are within components. In terms of the climate impacts that were of concern, we're talking here about temperature, extreme heat, heat waves, and extreme cold, precipitation, wind, and then some of these complex variables. And I mentioned the complex variables because some of these are extremely high impact, but very, very low probability events. So tornadoes can be a very big impact, but often don't happen in a region. But when they do happen, and if they hit something really important, they can be very, very severe. So these types of complex variables are very specific sometimes to a region. This all gets put into kind of a matrix or some sort of data solution. And in this case here, we have our climate events going across the side, and then we're doing a risk assessment within the spreadsheet itself. So what do some of the results look like? We go from things like extreme heat. So currently something like 40 degrees is not a really high risk, but into the future, just because of the frequency change of that extreme temperature, it becomes something that's a moderate risk. For this example too, we're talking about things like wind being a moderate, high, or extreme risk, depending on the distribution kind of orientation of the lines. And then the other example here would be ice accumulation. And while you would think with climate change that potential ice accumulation might change, depending on the future climate period that you're looking at, it may go up and then eventually plateau into the future. But in general, more precipitation in the winters and potentially falling around freezing equals more freezing rain instead of snow. In these cases, this meant going from a moderate to a high risk for some of these major areas. And so now I have a poll for you. So the poll question here is, which of the following types of climate events that have impacted your infrastructure are listed below? So infrastructure, services, or community. And feel free, you can select multiple ones here. We're talking about things like flooding, wildfires, heat waves, freezing rain and ice storms, or extremely heavy snowfall. We'll give you a couple of seconds here to fill that out. Okay, I think we can close the poll. And quite interesting results here. So seeing a lot of impacts from flooding, that's a common hazard, and also wildfires. So almost 70% of folks here have had issues with flooding, and 50% are saying wildfires. So that's becoming an emerging hazard here. Surely that's a great lead into our next piece with Curt, and he'll be speaking a little bit more about some specific case studies.
Well, thanks for that, Norm. I really appreciate the overview, and I think Norm did a great job of presenting how we might come into a client's operations and evaluate their systems for the threats of future climate. We're going to shift gears here for the remainder of the presentation to talk about two large-scale resiliency programs. These are case histories from the U.S. power sector. Again, my name is Curt Bjurlin, and I lead the power sector for environmental services at Stantec in the United States. And then really, we're going to, for this section of the presentation, we're going to be talking about power utilities. However, I know there are folks likely on the line that are associated with energy companies of all types, and perhaps with other types of companies. And the principles we're going to talk about here do obviously pertain to any type of company and their operations and their infrastructure. So when we talk about power utilities, there's a common theme. At the core of the mission of a power utility is keeping the lights on. And what I've done is I've pulled up 6 value statements that I took directly from websites of some of the largest utilities in North America, and you can see some common themes. Clean, reliable, affordable energy. Clean, safe, reliable, affordable energy. Safe, clean, reliable. Cleanest, safest, and most reliable. And of course, the last that I really enjoy is building a future you can depend on. That reliability of energy is at the core of the value of power utilities, and rightfully so. In this slide, you can see 5 of the more notable blackouts that have occurred in North America. And I'll just talk about these briefly. We don't need to go into the details here, but for instance, with the Northeast blackout of 2003 and the Northeast blackout of 1965, combined 70 million people were affected in those events. Of course, everybody remembers the 2017 Puerto Rico blackouts with 3.4 billion customer hours disrupted, and some parts of the island remaining without service for many, many months. Superstorm Sandy in 2012 led to over $70 billion in damages, 233 deaths across 8 countries. And of course, most recently, the 2021 Texas power crisis that left 5 million people without power for many days and led to directly caused 32 deaths. So as you can see, when the power goes out, when the lights go off, there are real world consequences, and those consequences can come in a number of different ways. Myself personally, my family was affected very strongly by the Northeast blackout of 2003. My brother at the time was running the IT systems of a large manufacturing facility in upstate New York, and that facility went down for a period of, I think, a week or 10 days, resulting in millions of dollars of losses. And a great number of people at that facility lost their jobs, my brother included. So when we look at the importance of resiliency and reliability in our power system, we don't have to look farther than our own families. Okay, now we're going to do a short poll, just a kind of a fun poll here. And the poll question is, have you lost power at your home or place of business for more than 5 hours at some point in the past 5 years? You can select home, work, both, or neither. I'll just give you a few seconds here to complete your answers. Okay, let's see what the poll results are. Okay, looks like 28% of the participants have lost power for more than 5 hours at their home in the last 5 years. So that's a fairly large percentage of the people on this call. And I'm going to tell you now why that is going to become a much bigger issue in the very near future. All right, we had a little technical difficulty there for a moment. So here's what's happening in the power sector and the energy sector at a larger scale. There's a tremendous energy transition that's underway right now. And I don't think it's an overstatement to say that in many ways the future is electric. Historically, electricity has provided important services in the commercial, residential, and industrial sectors. But what we will see in the future is that electricity will expand its footprint in those historic sectors and also begin to provide important services in the transportation sector. So imagine a future in which your heat is not coming from gas, but it's coming from an electric heat pump. Imagine a future where your transportation is not coming from gasoline, but it's coming from a plug-in electric vehicle. And then expand that outward to imagining all of your neighbors having the same services, your delivery truck drivers, your food service, your grocery stores, and so on and so forth. And you can understand, sort of at a glance, how critical reliability will become in that theater when more of our services, our energy services, are provided by electricity. So with that in mind, I'm going to talk about two case studies for leading power utilities in the United States that have undergone very strategic, comprehensive, and long-term climate adaptation programs. The first case study will be in the Mid-Atlantic region of the U.S., and we'll be looking at strategic undergrounding distribution systems with the intent to shorten restoration times from major storms. And the second case study will occur in the West Coast, and we'll be looking at a comprehensive program to prevent wildfires, in which that utility is changing vegetation management strategies, assessing weather and adjusting operations, and upgrading equipment. So to begin with, talking about a strategic undergrounding program, a leading power utility in the Mid-Atlantic region has engaged in a data-driven approach to speed recovery process after major storm events. This utility is focusing their efforts on tap lines, which, if you're not familiar with that term, are essentially the distribution lines that service neighborhoods, and which are prone to being impacted by tree branches, particularly in heavy storms. Now, by focusing in on those infrastructure resources, they are realizing both local and system-wide benefits, because it allows them to prioritize where their crews deploy and send those crews to other outage locations. They've determined that by doing this work, they've created a comprehensive solution that decreases the amount of work associated with these outages and allows them to come back online more quickly. In their public filings, they've reported that undergrounding 20% of the most outage-prone overhead tap lines can reduce the length of storm restoration by 50%. So it's really a very clear value proposition. Okay, how are they doing this? Well, there are 6 stages to their procedure. First, they're evaluating the infrastructure, they're designing a solution, they're securing easements, they're engaging in pre-construction activities, construction, and then property restoration. Now imagine as a power utility, talking again about these lines that directly service neighborhoods, you've got thousands and thousands of potential property owners to engage with. And in the map here, you can see just a depiction of one region of the system and the sheer number of people that are affected and the tracking of that information. The costs for this system have been reviewed and approved by the State Corporation Commission. And because all customers are benefiting, there are no direct customer costs for an individual project. So Stantec's been working on this program for many years, and Stantec is one of just a whole number of vendors working on this effort. It's a phenomenal amount of work that's necessary to achieve this kind of level of adaptation. The types of work that we're doing include project walkout, centerline review, pole audits, landowner research, plat development, negotiations with landowners, permitting design, and project stakeout prior to commencement of horizontal directional drilling. Now, as you can imagine, with a program of this scope, you've got a tremendous amount of information to manage, and managing that in an effective manner is critical. The screen that you have in front of you shows a GIS data interface that's available to all of the project participants on smart tablets, iPhones, handheld devices, and so on. And it allows at a glance information on the status of individual properties and the work that's planned on those properties. This program's in its 8th year with over 1,350 miles of outage-prone overhead tap lines having been converted. And the program has an annual investment cap of about $175 million. And to date, $545 million has been spent in capital. There's a legislative sunset clause for this program in 2028, and the original intent was to convert 4,000 miles of these outage-prone overhead tap lines to an underground location. Everything that I've presented here is in the public register, and this information, in fact, came directly from the Utilities U.S. Securities and Exchange Commission annual report from just February of this year. So it's up-to-date information. The important takeaway on this program is that to put in place an effective climate adaptation program requires significant investment and a long-term commitment. Okay, shifting gears now to the West Coast of the United States, let's take a look at what we've all seen in the news, seems like every week now, and that's wildfires. What you see on your screen is the 2020 Fire Siege Report, a public document that's released by the California government. And in that document, you have some very alarming statistics. As we know, wildfires are a major source of disruption, cost to the taxpayer, and a risk to life and property. But you may not have known that 5 of the 6 largest wildfires in California history occurred just last year. One of those fires affected over 1 million acres. Surprisingly, it's estimated that approximately 50% of the wildfire damage that has occurred is directly linked to climate change. And this is due to an increase in the number of dry, hot, high wind days, a doubling of those types of events since the 1980s. And there's also a change in precipitation that has led to an increase in vegetation that then dries out and creates more tinder. Now again, a leading power utility on the West Coast of the United States has embarked on a multi-year endeavor to expand their efforts to prevent wildfires. And I think if you were to take a careful look at any of the utilities that are operating in this area, all of them are addressing this issue in some fashion or another. For this particular utility, they report in their public documents that 1/3 of their electric lines are in high fire threat districts. That's about 5,500 line miles of electric transmission and 25,500 line miles of distribution. They report on their efforts to try to reduce the threat of wildfire in annual wildfire mitigation plans that are publicly available. They really crystallize their mission in 3 statements. They're seeking to reduce wildfire ignition risk, enhance wildfire risk situation awareness, and reduce the impact of public safety power shutoffs. And the strategy is simple. They're focusing 80% of their work on the top 20% of highest risk circuit segments or fire rebuild areas. So let's dive into some details on these 3 objectives. Reducing the ignition risk. They're doing this by enhancing their vegetation management program, increasing asset inspections, they're hardening certain types of infrastructure, they're undergrounding other types of infrastructure, and they're replacing assets where necessary. In terms of situational awareness, they've installed over 1,000 weather stations. In fact, they installed 400 weather stations last year alone. And they've augmented their system with high definition cameras that allows them to do real-time assessment of current condition. In terms of reducing the impact of public safety power shutoffs, they're looking at sectionalization of their distribution system, transmission line switching strategies, setting up distributed generation and microgrids, establishing community resource centers for the public, communicating, and increasing their community partnerships. And as we saw earlier, when the power goes out, there are real-world consequences. So utilities think very carefully before they turn the power off, even when it's an imminent safety risk. In this particular program, Stantec has been working with the client to conduct inspections of electrical systems and provide mitigation design recommendations. We're reviewing proposed work locations and identifying environmental constraints, facilitating schedule management with a greater team. We're micrositing work locations and designing access routes that minimize impacts to the natural and the built environment. We're performing agency notifications and outreach, field surveys, and we're preparing permits and providing compliance assessments. And again, we're one of just a whole large number of service providers that are helping this utility achieve their objectives. So those were two large-scale programs that are happening right now in the United States. And I'd like to leave you with a couple of key takeaways. In Norm's presentation, he discussed how climate uncertainty requires a regular reassessment of risk. And I want to stress here, regular reassessment of risk, because as you saw, the past is not necessarily the future when it comes to a changing climate. He also presented an example of the accepted processes that are available today to help with conducting climate risk assessments. And as we saw in his examples and in the examples I presented, the exposure that energy companies, or really any types of companies, have to climate risk depends on the types of infrastructure they operate and the location of that infrastructure in the broader context of the geology, the geography, the climate, the people of the region. Energy companies have already begun this effort of adapting their infrastructure to a changing climate. And climate risk mitigation programs require significant capital investment, stakeholder engagement, and expertise. And I'd like to leave you with a thought before we go to the question and answer period. As you saw in both of those examples, the investment is significant to effectively adapt an existing system to a changing climate. And the time it requires to implement that kind of program can be on the order of 10 years, 15 years. But we also saw in Norm's graphics that the climate is also changing on that same timeline. And so really the takeaway here is that every company that wants to have a resilient and adapted infrastructure needs to begin assessing that infrastructure with respect to a changing climate today, and also needs to understand and communicate throughout the company's decision-making process that the implementation of an effective adaptation program can take up to a decade or longer, and it will be a work in progress throughout that entire period as the risks are reassessed and the adaptation strategies are changed to adequately mitigate those risks. And with that, we'd like to shift gears now to the question and answer period.
Thanks, Norm, and thanks, Curt. I thought both very good, informative presentations. Got a number of questions from the audience, and I think there'll be some useful discussion coming up. So I really appreciate the insights that both of you bring. So just a reminder, so we're live through till top of the hour. If you do have additional questions that come to mind, you know, throw them our way, and we'll do our best to respond to them. So if you just give me a second here, and I'll pull up a couple of questions. So first one, how do you assess the likelihood aspect of the climate risk matrix? And this sounds like a Norm question to me.
That's a great question. Thanks, Jason. And so the likelihood is governed essentially by understanding what the historical climate has been doing and what the future climate projections are coming from. And so while we're binning it into these scales, you saw an example here of a 5.1 to 5 ranking scale. We're looking at what the change in return period of key events might be. So if you think about that flood example, something that's a 1 in 100-year event might be a 1 on our scale, whereas something that's a 1 in 2-year event might be a 5 on our scale. And so we're looking at how that's changing using climate projections and climate modeling, and a synthesis of all different types of data sets from IPCC, from the governments, both in the US and Canada, and from historical data that's been observed to understand where we're changing from.
Thanks very much, Norm. That was good. Good response. That makes sense to me. If it makes sense to me, I think most people in the audience can probably understand it. So we got a couple of questions that relate back to renewables and the role of renewable power, and how that plays into resiliency. So first question, how important do you consider microgeneration as it pertains to climate risk and resiliency? And I might just, you know, kind of piggyback that with another sort of related question, and that's how do you see the growth of renewable power affecting resiliency planning? So I think related questions, if you're able to tackle both of those at the same time, Curt.
Sure. So microgeneration, microgrids, distributed generation, renewable energy. You know, as we all know, those forms of energy are becoming ubiquitous in our systems, and grid operators and utilities are adjusting their operations to accommodate the integration of distributed energy resources. The impact on resiliency, that's an interesting question, Jason. We know that some utilities are looking at distributed energy resources and microgrids as a way to increase the resiliency of their systems. However, when you look at a system as a whole, the types of climatic events that occur that Norm has been discussing could differentially impact certain types of generation. So let's just say high winds, and you have high winds with extreme wind loading. You may have distributed energy resources such as solar panels on houses, ground mount systems. If those systems are not designed appropriately for the types of wind loading that occurs in the changing climate, then you could be increasing risk in that particular case. So I guess that's kind of a long answer that's a non-answer, and to say that the devil's in the details. Certainly, the energy system's changing, and DERs are becoming much more common. And I think the answer is that in order to know on a case-by-case basis what that will mean for resiliency, there needs to be a climate risk assessment.
Yeah, that's great. Thanks, Curt. Good response. I just want to remind people again, someone just made a note of this. If you do need to ask a question, or if you want to ask a question, go to the webinar question box. Like I said, that should pop up on your screen, and you can just type that in. It'll show up on my screen, and we can ask away. We got about 8 or 9 more minutes before the top of the hour. So next question. And I'm not sure if this is a Curt or a Norm. Could be both. You know, Curt, you might want to start this off, I guess. Or sorry, Norm might want to. How can climate risk assessments be integrated into new proposed projects, infrastructure projects?
Yeah, I can start it off, and maybe Curt, you can join in on it. But so depending on your location, there are ways already, actually funding wise, that allow you to leverage essentially federal funding. Even if you're at the design or at the pre-design or feasibility, even a site selection process. And really what it comes down to is a level of detail that you're going to go into in your assessment to begin, and then kind of expand as you further on your design. When it comes to funding, for example, too, in Canada, we have the process called the climate lens that allows essentially projects with over $10 million of committed funding from the feds. You have to go through a climate lens, which looks at both GHG and climate resilience impacts of the project. But at the same time, you may not know what the picture of your infrastructure is going to look like when you're doing your application. And so we've worked in many different situations where you can either use a similar type of asset, a similar type of, so if you were building an arena, for example, or if you're building a pipeline, you might use one that you had a similar example of that might have similar conditions or a similar region. A lot of times what we're doing when we're selecting climate parameters or infrastructure is basing it off of almost a conceptual model of what each of these components should be, right? There's lots of commonality between all the different types of assets there, but we're really focused in on the local climate and that being the driver of the risk. Oh, Curt, if you have any.
Add on to that, Jason. Now, there's certainly formalized process, and Norm's talked about that formalized process to evaluate climate risk for new projects. But there's also the human component, and sometimes it's as simple as the project manager asking the question, looking at infrastructure and saying, you know, that new piece of essential equipment looks like we're planning to put that in what has been considered a 100-year floodplain. Will that be a 100-year floodplain in the future, or is that going to be a 5-year floodplain? And how critical is it that we that piece of infrastructure continues to operate in a flooding event? And those kinds of questions, so I don't want to overemphasize the systematic evaluation, because really each and every project manager and or team member for a new infrastructure project has a responsibility to actually ask that question. You know, we can't claim ignorance anymore that there's a changing climate and that we're addressing that in some fashion. So it's as easy as asking the question, and then of course, you know, finding the experts to help you answer that question.
Yeah, that's great. And thanks both Norm and Curt. And I mean, obviously Stantec's in a position to support our clients in evaluating where and how those climate risk assessments would unfold. So another question that's just come in, and this I would say is a norm question. Do you calculate a cost to the climate risk? And then it just goes on to say, ESG investors are requesting public companies to identify climate risks and estimate the cost to disclose material risks.
This is a really excellent question. Yes. So at the end of the day, a risk score, if you show it on the screen, it doesn't really mean much. We need to translate that into what does that mean in terms of an impact? Is it dollars? Is it human impact? Is it, so yes, we do calculate that. And as the world is kind of waking up to the reality of climate change and climate change risk, we're seeing, as you're saying, kind of public companies needing to disclose this to their investors. Oftentimes when this is being done, we're associating it with kind of the replacement value of the assets that you have physically. There's kind of two components here. There's the physical risk, and then there's a risk posed by transitioning to a lower carbon economy. What does that mean? Is it an opportunity or is it a risk, right? So on the physical risk side, we're assigning it with how severe is the impact and going through the whole risk process and understanding the cost that might be on each individual asset. So yes, we do that.
Yeah, that's great. And I guess sort of related to that, I heard a news item that came in today related to oil sands operators and the challenges with insurance. I know that's, you know, perhaps indirectly related to what we're talking about here. So so definitely salient question for sure. I've got another one here. Looks like we have a couple more minutes. And this might be another Norm response. Future climate projection comes with uncertainty. This uncertainty varies from model to model. In such cases, how do you choose which climate model to use and how many climate models, or which or how many climate models to use?
It's a good question, and it's a really complex one. So I'm trying to think how will we simplify that for a couple of minutes here. Most of the time, we are often using kind of the best recommended models, particularly for operating within Canada or for operating internationally. So we're using an ensemble of models, and rather than a single model to represent, you know, climate change impacts. Within Canada, one of the data sets that's here is kind of this really nice downscaled 24 model set that the federal government has that's available. The other one, if you're working in the US, there's a whole different set of downscaled data sets as well. But as is noted there, the uncertainty is different from model to model. So typically there's a whole bunch of procedures that we go through to make sure that we're handling uncertainty. But one key thing here for the process here and the resiliency and the risk assessment process in particular is because we're binning things into these kind of 5-point scales, we're hopefully handling some of that uncertainty by kind of allowing for a range of probabilities within each bin or likelihoods within each bin, so that one bin may go from something that is something extremely infrequent to something that happens 25% of the time across a period. And you would have kind of graduated bins as well going up. So on the likelihood side, that's how we handle it. I know that's complicated, and if anyone is curious there, then feel free to reach out. I'm happy to talk more about it.
Yeah, thanks, Norm. Thanks for keeping that succinct. I know there's a lot to say around that for sure.
Yep.
So we're just wrapping up here. We got about 30 seconds to the top of the hour. Just want to say thanks, Norm, and thanks, Curt, for fantastic presentations, great insight and great responses to some really good questions. And just to respond, or just to remind the audience that feel free to reach out with any questions, follow up. I know we're all happy to help out and to respond to any questions that you might have. So thanks everyone, and have a great Thursday. Thank you.